Hello everyone. Today I thought I'll show you how I took this snippet of code that does a very specific task, which is the rotation of a point cloud along a given axis, which is the x-axis. How I took it from running 10 plus seconds to 1 to 2 milliseconds. Yeah, that's around 10,000 times faster. In it we have the main file, which if we do .h -h, we can have our options, and our options are the number of iterations. We'll do one iteration now because I created it in terms of like a benchmark that runs iteratively and sums up the runtime and then delivers you the mean of the runtime. So yeah, I'm gonna include the pure function, so -b, the number of point clouds. We're gonna do a single point cloud since we're doing a single iteration, and I'm gonna include the GPU, yes, because we have an actual GPU here. And yeah, it gave us some statistics on the random point cloud it generated. This is why I'm doing just one iteration, because the pure Python function, so Pi rotation CPU, is taking 21.5 thousand milliseconds, so almost around 20 seconds. In comparison, the rotation on the GPU is taking 2 milliseconds. And yes, I'm actually doing a correctness test that tests the output of the GPU, and the Python code is exactly the same, one-to-one. And I'll show you the code that does that in a second. 20 seconds, that's painful. So yeah, if I'm gonna run it again, we're settling in after 100 iterations, we're settling at 20 milliseconds, 20 milliseconds, 32 milliseconds, and 1.8 milliseconds. Remember guys, we were at 20 seconds. So yeah, let's jump into the code. And in our main function, we first print the stats that we've seen. We test the correctness, and in the correctness, basically, I call the first function, the second notice here I'm doing a copy so that we are as fair as possible. I'm doing a deep copy of the point cloud before passing it to each function. So I'm doing the first, second, third, and fourth option. And then I have this function, I created it to do element-wise equality between the 2 point cloud in order to make sure that it is doing exactly the same job. And the reason I have this, and I'm not doing like a NumPy function or a double equality, is that these are floats, and floats can never be equal. You cannot do this. You can do this, but it will be always false, most certainly false. At every iteration, so we have a list of PCLs that we've created, randomly created. We randomly pick one of them. So yeah, we just keep on iterating, and then we just print the means of all the runtimes. Get back to our benchmark. We can see that we have 1, 2, 3, 4, 5 options. One is called JIT rotation CPU, which stands for just-in-time compilation. We're doing just-in-time compilation to Python. Here we have a C version, so it's actually written in C, and we'll look at the code in a minute. It's actually parallel C, so it's threaded C. Then we have another version of the C function, which is contiguous, which is just like one thread. We have a GPU version, and we have the forbidden purely Python version that will never run again because it's just insane. As Prime says, I don't know if you know who the Primeagen is, and if you don't know him, what are you doing and why are you watching me instead of watching him? But worst thing that you can do in Python is run a for loop, and here we have two for loop, actually two nested for loop. The 5 versions, and they are, we have first Numba, NUMBA, and Numba is a Python JIT compiler. What it does is that you give it Python code, and it gives you very fast Python code. And actually, it's very simple to run. It's very simple to use. So basically, if we do this, like if I comment this line, now this is a Python code. If I return this line, now this is compiled code. The only trade-off to not to using like Numba for for compilation is that it doesn't support most of the Python. The second option I'm gonna talk about is C. So yeah, I wrote actual function in C. Actually, two options of this function. One that just runs in one thread, and one that is parallel. And then I'm wrapping the code like this is a Python function, and it's calling to the DLL, so CDLL. This C types library, it's a built-in library in Python. It allows you to link into this library file that the build.sh spits out. So we have one pure Python function, which is this one. So where it does that pre-computes the sin, the cos, it takes the width and the height, and two for loops, and we just apply the rotation to the point cloud. I actually didn't talk about the rotation to the point cloud, so yeah. So basically what a point cloud is just 3D data represented within an array, and I have this example in here that I have, it's a Medium article, and within it there is a so basically this is like what a self-driving car would see in 3D, not with the cameras but with the LiDAR, which is like a 3D data 3D sensor basically. And yeah, this is what a point cloud is, and sometimes we need to do some rotations and mathematical or trigonometrical like transformations on the point clouds to change perspectives and change planes and stuff. In our case, say this is a 3D object, we have the Z and Y and X axis, and what we're trying to do is we're trying to rotate the whole point cloud along the X axis. This is what we're trying to do, and this is the GitHub repo, by the way. So we went through the pure Python option, the two C options, the number option, and we have one left, which is the GPU option, and which is our fastest option. And for that, we're still using Numba, but inside Numba we have also a JIT compiler for CUDA. Believe it or not, we're basically using the same function. By the way, like this is the pure function, the pure Python function, and this is the Numba function. See how similar they are? We just had to do like instead of using the range, we have to use the numba.p range in order to parallelize. So, okay, for the CUDA code, it's a little bit more involved, but not that much actually. I'm not gonna go into details about the grid and dimensions and block dimensions and stuff. These are like CUDA specific terms, but I left a very great like reference here. So yeah, these are all the options that I have for you. You can explore the code furthermore, but yeah, this concludes my love-hate relationship with Python. I hate how slow it is, but I fucking love how fast I can go through tasks with it, and when I need to go faster with Python, I can. And they have so many options. As the Prime says again, Python could either be like the best language ever or the worst language ever, and for me at this moment is the best language ever, because I can really make it fast whenever I want to, and when I don't need to make it fast, I'm really fast typing and producing stuff in C. Yeah, so that's basically what I wanted to talk about now today. So yeah, thank you for watching, and I'll see you in the next video, I guess.